Okay, recording in progress. Okay, the next thing I've got, keeping in the Embarcadero news, is another item on their blogs, which tells us that Rad Studio 11 is coming. Some people were waiting for 10.5, but since Microsoft and Apple have both decided to go up from 10 to 11, Embarcadero is doing the same thing. So no details so far, apart from what's already been announced for 10.5. But it's going to be, you know, they're starting to rattle the marketing cage.
You can still get on the beta if you want to.
Yes.
I've signed up. I got my key yesterday.
All right. Okay. Yep. So if you pop over to the Embarcadero site, there's some details on how you can sort of do that if you have a registration. I did see somebody ask, is it available if you're on the community edition? But I think the answer is no. Dear. Onto ZDNet. So Uber's found to have interfered with the privacy of over 1 million Australians. They had a data breach back in 2016, which was, I think, international in scope, but they failed to disclose it, as their good companies should do. And they, in fact, they concealed the breach and they paid a hacker to keep it quiet. So it's pretty poor corporate morals going on there, I think. So, and also on ZDNet, Google Clouds to launch a new region in Melbourne. So if you're a Google Cloud user and you've got a business and you'd like to have a Google DR site that's geographically located away from the Sydney site, then you probably already know about this. But if you didn't, like me, then it's news. Something else I've found about this when I saw this article was seeing whether the Google Cloud is able to carry protected information or information protected level, and apparently it is and has been since February. So I know that Microsoft Azure has a Azure, as the Americans call it, Azure as we call it, have a they've got the protected tag on some of their sites. Security news is what I like to throw in some of that. This comes from the Security Week website, and earlier this week carried the news that the US have charged 4 alleged members of the Chinese hacking group, and they officially accused China of the Microsoft Exchange attacks, as did accused by the United States, European Union, NATO, UK, Canada, Australia, New Zealand, and Japan have all sort of put their weight behind this. And then, of course, there's the usual slew of patches that come out. There's been a whole bunch of issues with Windows, especially Windows servers and print services. So make sure you do all your updates, turn off print services when you don't need them. And not to be outdone, Apple have also had a few releases. I've updated my iPhone twice this week. 14.7 came out, and then 14.7.1 came out, I think it was today or yesterday. There's a big update, 11.5. I'm going to be updating to 11.5.1, which is the latest one. So that's the security news. Does anybody else have any news they like?
Have you received an email from Google today regarding Google Drive?
No, I don't have a Google Drive.
I've just put it in here into the chat, because I'm using Google Drive quite a bit.
Yep.
So where is actually, which files will be applied?
Yep.
To see file security update, yeah.
Oh, yeah,
And then there's
I
actually,
recall seeing that. Yeah. Yeah. Not remove the update. Should not be cancelled. Da, 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 da. Yeah, I did see something about that, but I don't use it. You know, I've got Dropbox, I've got the Apple Cloud, I've got the Windows one. I don't know. So many clouds out there. We're all looking for blue skies. So thank you for that. I'll stick that in the notes as well. Okay, now let me have a look. I asked, we've got tonight's presentation. We've got Dr. Hilary Stewart Williams, aka Hill, who's going to be talking to us tonight. And I just asked Hill today if he had something that he could share with us about his long and industrious career, and he sent me a very nice long email, which I've sort of condensed. So having sent me such a long email, I would be remiss of me not to give Hill a proper introduction. So he graduated in archaeology and geology from Bristol University in the UK in 1976. I was 16 at the time, Hill. Worked in geophysical processing and then moved on to exploration geology in the Canadian oil industry. That's not the snake oil industry, that I am assuming that's the real oil. Then a stint back in Blighty as an archaeologist looking after the museum systems for Jersey. Obtained a PhD on stable isotopes from McMaster University, which is Ontario, Canada. I used to live near there in Rochester, New York, and I can attest it gets pretty cold, lots of snow. Then it was back to the old dart, University of East Anglia in England. So that's a bit of tautology on my behalf. Finally came to his senses and moved to Canberra to work on stable isotopes in the physiology group at the Research School of Biology at the ANU. Allegedly, he retired in 2020, but for some reason he's still working. He's got a programming rap sheet that includes Fortran Basics, Turbo Pascal, C Assembler and Prolog. He's actually missed out Delphi, which is kind of...
Oh, well, I was dealing with the early ones.
Ah, right, okay. And he's been computing on all kinds of computers since 75, big uns and little uns. And tonight he's going to share with us some experiences on some of his little uns. So I'll pass it over to you. I believe you can share your screen.
Okay.
Oh, hold on, I've got to turn that button on. There you go.
Okay. Now, how do I do screen sharing?
Is there a button at the bottom, the bright green in the middle?
No, it seems to have disappeared. I think this is because when I bring up the PowerPoint, it overwrites it. Okay, well, let's see what happens. I'll do my best. So let's try sharing this screen. Share.
Yep,
and then
that's happening.
And then I'll try doing, then I'll go to slideshow. How's that?
That's wonderful.
Perfect.
Slide. Okay. Okay, now I think I need to go back to the beginning. Okay. Right, you should see a title slide.
Correct.
Yes. Yes.
Okay, cool. Right. Okay, so this is just kind of a bit of a miscellany. I started off looking at real-time computing and then got distracted into thinking about things in the past. So this is just a load of rubbish I'll skim through, basically. Went back to, oh, let's get rid of this. So I was thinking about, yeah, I was thinking about the early computers. And I was thinking about IBM 360, and I was thinking, well, was it I think it must have actually started off as a single task computer. I think it was only later on that they developed sort of, I don't know about multi-threading, but multitasking anyway. This is one of my first computers. Did anyone have one of these guys?
No.
Nope. No, it was actually, it was a pretty cool machine. I thought it was a very nice piece of styling, very much the same as the cars of the period. And if you didn't like the computer, you know, there was always Isaac Asimov to sell it to you. So,
Was that before he went to Sri Lanka?
was that him, or was that Asimov, or was that the guy who wrote Fall of Moondust?
I thought it was Isaac.
Arthur C. Clarke.
Ah, yes, you're right. Sorry,
Yeah.
my fault.
Yeah, no, I think
Isaac.
Asimov's name has stayed clean, surprisingly. Anyway, then we got these guys.
Oh, yeah.
We used quite a lot, and as I've said here, they were almost too powerful to package. You know, the little buttons were kind of pokey, but the machine itself was quite powerful. It would have been better with a larger keyboard, but at least when the 58C came out, it remembered what you'd put in, which was a big improvement over the 58. And they had a good advertising campaign too. Didn't involve Sri Lanka, but I think they're probably grateful they're not selling anymore, given Bill Cosby's current reputation. And then these guys, these were quite powerful. You could buy various bits that plugged into them. They won a design award. So I'm just sort of thinking about all the ones that sort of moved along. Then my first real computer was a PC Junior, which was as I say, there was an 8088 at 64K of RAM and would read both sides of a 360K disk, which was a distinct improvement. Then we got to task swapping with things like Desk View, but I don't think it offered real multitasking. I think it was more just a swapping environment. It was still pretty fancy in its day. I remember when I first saw it, I was quite impressed. And then Windows 386, which was presumably non-preemptive like most versions of Windows. I had this as well. And then finally, OS2 Presentation Manager, which was preemptive, but there was there were add-ons you could get to make it real time or make bits of it real time, because I remember it was used for things like air traffic control and that sort of thing, but it was hard to build a full real-time system with OS2. Just thought I'd note this, came across it while I was doing stuff. Anyone else remember this book, or is it too old for you all still still reading Famous 5 at that time? And then now, of course, we have things like the Raspberry Pi, where we have multi-core processors and preemptive multitasking. Just sort of thinking about the evolution of computers over the years.
That was a jump.
Sorry?
That was a jump.
You mean going from that to the Raspberry Pi? Yeah, it is, isn't it? Quite a jump in cost as well. And running OS2 is pretty expensive. So that sort of brings me to the real-time aspect of the thing. This is one of the first electronic fuel injection systems. Now, a real-time system, it has to do what you want it to do exactly when you want it to do it. So the early versions like this are, as you can see, not digital at all. It's like a spares box from a radio. And so, I don't know, can you see my mouse? Yeah, you probably can. Can you see my mouse?
Yes.
Yep, okay.
Yes.
So it was actually quite a clever system. It had this guy up here that sensed the vacuum in the engine, and it got the timing from a mechanical distributor, and then it worked out what was required from the fuel injectors on the basis of those inputs and temperature and other things. And it had just enough guts to fire them in pairs. It didn't fire it each one on its own, but it fired them in pairs. And the mixture that it produced was pretty good. It was rather an expensive system, because this guy here, because this whole system was sort of, basically as you built it, the pressure sensor that it relied on had to be very carefully calibrated and accurate. It was a very expensive piece of kit. But for all that, it was quite an amazing system for the late 60s. And it was originally sold as Bosch Jetronic, and later became D-Jetronic when they wanted to differentiate it from their other fuel injection systems. So they worked through various manifestations, one of which is K-Jetronic, which is what I'm looking at replacing on a car, which has basically no electronics in it, although it's later than this guy. And then, of course, so this was an example of one of the cars that ran that D-Jetronic system, which is a Porsche 914. But some of the VWs did as well, like the 411 and the 412 ran that injection system. But as you can see, there's no problem with real-time processing because it's basically just electronics. There's no digital component to the thing. And so the next big jump sort of came, I guess, the late 80s when they began to bring out Motronic, which was fully digital. And so it relied on programming to make it work rather than on changing a resistor if it didn't work right. And this, of course, did have to be real time. So it had to be fast enough that when you tell it to run a spark or inject some fuel, it does it. Quite expensive, quite specialized. Okay, well, what can we do these days with relatively cheap computers to achieve that same kind of thing? Well, the first thing that came to mind was this, and that's because the Beaglebone is always advertised as being a computer that will fit into an Altoids can. So this is the Beaglebone I've done a fair bit of work on. It will, there's a new version with wireless, but it will run, it'll run Lazarus just fine. But I'll come back to what makes it special. As you can see, it's fairly powerful. It's got 4 gigs of RAM in basically a multimedia chip that's mounted on the board, which is this MMC thing. And then it's got 512 meg in memory here. So that's the multimedia mounted, and that's the 512. It's got floating point accelerator. It can be a USB host, which is very handy. Got Ethernet. It's got a micro HDMI output, which is a nightmare. And it has loads of digital outputs that you can pin things into down the sides. Now, what's special about it is this, the 2 32-bit microcontrollers that are actually part of the computer package on the board. So it's like having a Raspberry Pi with 2 much faster Arduinos attached to it. So this is just a map of what it looks like. So there's the ports and the USB, Ethernet, power supply, and so on. Don't really need to dwell on that. If you want to learn more about cooking it, about programming it, you can go to the Pru cookbook. As far as I can see, programming the Prus, the programmable real-time units, has to be done in C, and TI supplies a free C that you can use for doing that. But also, as far as I can see, I should be able to speak to the PRUs from Lazarus. So basically from Delphi-like language running on the conventional ECU, which is a Cortex A8. But this site is worth visiting if you want to know more about the board. Why would you want to? Well, here's a table of performance. What they did was they basically generated a wave and saw how fast they could generate it with particular processors. So the Raspberry Pi is right down the bottom here at 0.15 megahertz. And then some of the faster stuff on the recent Pi 4s, you get up to 3. Then when you go to the Beaglebone and you run it on the Pru, you get nearly 17 megahertz. It's much, much faster than any of the options offered by the other chips. So this is what the architecture of the chip looks like. So you have a Cortex A8, then you have the 2 real-time units, which have memory of their own, but also have shared RAM, and they can communicate through shared memory and other things with the main processor. So why would you want to do this? Well, say, for example, you were building a fuel injection system, you need something with a lot of brains, but then you also need bits of it that will respond instantly to drive the injectors and the ignition and everything else. And so this offers the opportunity of doing the whole thing on the one board. The code for the PRUs is pretty simple. This is an example of it. And really, once you've got everything set up, it's just a perpetual while loop that's doing a pin in and a pin out. That's how they're generating that 17 megahertz waveform. Obviously, we'll do much more than that, but that just sort of shows that at the basic level, it's not a complicated thing to deal with. So this little robot, for example, uses a Beaglebone blue, which has a little bit of stuff on it extra to the Beaglebone black, and makes it suitable for robotics. It's got accelerometer, temperature sensing, and other things. And this robot runs around on these two wheels balancing itself. It couldn't do that without the responsiveness of the PRUs to provide the feedback and drive the pulse width modulated servos that keep it upright. So the pulse width modulation is all done in software by the PRU. It's not, they don't use a generating chip at all. It just computes fast enough to maintain pulse width modulation for the 8 servos that are involved. So it's a very rapid piece of kit. Now, I started to work with the Beaglebone, and then I got a bit late on time and decided to take a shortcut because I figured, well, all I'd end up with would be like a flashing light or something. It wasn't going to be that impressive anyway. So I moved across to doing it with Arduinos. And what I wanted to do was to write software with an Arduino that would replace a distributor, or at least replace the advance on the spark function in a distributor. In an engine, as the engine rotates, as it comes to the top of the compression stroke, there's a spark that ignites the fuel layer mixture. And that spark has to arrive at exactly the right moment so that the engine doesn't produce pollution and produces maximum power. If it arrives too early, you waste power, too late, you waste power. And the fuel layer mixture burns at different speeds, but takes a finite length of time to burn. So as the engine RPM go up, you need to light the mixture sooner for it to actually be combusting at the right point in the cycle of the engine. So what a typical distributor does is that as the RPM increase, it starts to ignite the spark earlier and earlier, often till it reaches a plateau like this. So I thought, okay, now you can't predict the future, but what you can do is you can set the mechanical ignition as far advanced as it will go, as though the engine is running at 7,000 RPM, and then you delay when you're going to actually produce the spark when it's running at lower RPM. And you can do all that with software using real-time computing. So if you look at a more modern system, rather than being like this old system where it's simply RPM and degrees of advancing the spark, on modern systems, it looks at load and other things. It's a much more complex function to decide when it's going to ignite the mixture. So you can obviously do that in a computer. It's much harder to do in a purely mechanical device. So here's what I actually did. This is actually what picks up the spark from the distributor in the engine. Don't really need to worry about it too much, but I pick it up as the signal coming out of the distributor, and it then goes through a transistor and through an optocoupler. The optocoupler is because you're running very noisy, often high voltage signals on this side that you need to protect your electronics from, or it'll fry them. So it goes through this optocoupler, and what happens is a little LED in here flashes every time it receives a signal, and then a little resistor on this side permits current to flow every time the LED flashes. So there's no connection between the low voltage side here and the high voltage side, which is connected to the engine. Same thing that's used in like mass specs, or my mass spec boards have a high voltage side, optocouplers, and then a low voltage side. So what I do is I take the signal coming out of the optocoupler and I can feed it into an Arduino. So I didn't want to have an engine running on my desk for various reasons. So I'm generating my engine signal in this Arduino, and it generates a pulse, and then it calculates what delay I want on the spark, and it uses 8 of these GPIO lines along here to send a bit as a parallel signal across these wires to the other Arduino, because it's much faster than trying to do it by serial. And then it has a couple of other lines that say, I'm ready to write, and the other one says, I'm ready to receive. So this is the master that generates the signal. And this is the slave at the other end, which is a cheaper Arduino that simply runs the program that decides how that delays the spark. It receives the signal coming in saying spark, and then it receives these 8 data bits that go together to make a byte. And from that, it determines how much to delay the spark before sending out to the spark plug. This is what the whole thing sitting on my desk looks like. So there's the 2 Arduinos, a breadboard to connect them together. This is an automotive oscilloscope, a cheap one because they won't throw too much money at this operation. And these are the signals that are being produced. So the yellow signal on channel 1 here is the signal saying I'm sparking, and the blue signal here is the signal that goes into producing the actual, each of these spikes becomes a spark at a spark plug. And as you can see at the RPM I'm at, it's slightly delayed from the timing signal. So, so here's what it looks like in detail. So this is sort of about idle. So here's the timing signal coming out of the first Arduino, and the turquoise lines here are the signals which will actually be converted and sent to the spark plugs. As you can see, there's a substantial delay. Each of these grid lines is 10 milliseconds. So there's a reasonable delay between when the signal comes in and when it actually fires the pulse. So as we increase the RPM, you'll notice there are more. So we're now getting about one pulse every 10 milliseconds, and the delay on the signal is being reduced because you remember, as we speed up the engine, we want the spark to advance. So this is maximum advance, and it's getting closer to it. And then we go to 3000 RPM. At that point on that Porsche timing curve, there's no delay between the timing signal and the spark that's generated by it. So the 2 lines fall on top of each other, and we're now producing about, I don't know, 1 every sort of 6 milliseconds or so. And then when we get to about red line on the engine, then we're now producing 3 sparks every millisecond with no delay between the triggering signal and the actual pulse going out to the spark plug. Does that make sense? Any questions? Everyone totally bored yet?
The only question I would have at this stage is, how do you detect that you are on a measurement unit and not out in the wild with your car? Because that's what Volkswagen did, right? They detected that they are now measuring. Have you built that into your software too, to detect that you're now checked by the authorities, and now you're offline again, and you can run as fast as you want?
Well, I could put an accelerometer on the Arduino, and I could just say, well, it's not moving. We'll just go to optimum mode. Okay, I can just quickly show you the code. It's not very interesting, and I'm afraid it's in C. Now I may have to, I think I might have to stop this.
Question.
I'll just stop this screen share, and I will fire up Arduino. I'll show you the master first, I guess. Yeah, that's the driver. So we'll bring that over there. And what have I done now? Screen share, and I want to share this one.
Question.
Yep.
Having the 8-bit lines connected, is there any issue with the what is it, Arduino sending, the 8 bits in synchrony? I guess they're all clocked together, are they?
This was a rather crude attempt. There are actually bits, there are libraries you can get out there to send them much faster. I just used the basic digital read and digital write functions. I think probably one could, well, I could send a byte, but it wouldn't probably make much difference in the end.
But it's no problem, like, you know, having the different 8 bits, keeping their coherence as a group from endpoint to, they all travel over together.
So I go through the code and then maybe it'll be a bit more clear how I'm approaching it.
Oh no, carry on, it's no problem, thanks.
Yeah, sorry, I don't know quite what you're asking me. Okay, so here I set up my definitions, set up my variables. You have to tell each of the pins what mode you want to use it in. So this is the boss. So most of them are going output. This one here, pin slave ready, is what I will read to know when the other Arduino is ready to receive a value. And I'm using input pull up, which means that I'm using a resistor to provide a positive voltage to the line, so it will sit high when I'm not pulling it down. Okay, that's the normal practice to do that. So I start my clock. Now, what I do here is I get the time that I'm starting the cycle, because I want to generate a pulse that corresponds to how long it would be between each spark for the running engine. So I'm doing that. So this one there, while micros, it reads microseconds. That's what micros does. It returns microseconds. And I'm just running through it until I've run for as long as I want it to run between firings. So I set the clock, that I set the spark outline low. So what that does is I've pulled it down against the resistor, and I will then sit with the line low for as long as I want that triggering signal to stay low to trigger the other Arduino, and then I switch it back to running high. So this is my very basic logic for controlling how much the spark is retarded, in other words advanced, but in this case retarded because I'm working backwards. I sort of apologize for the go-tos and sort of don't. I think it makes a very tidy structure in this case. I know my reputation has been permanently smeared by that. So I look to see on this one GPIO line whether the slave is ready to receive. If it is, then I set the line saying that I'm active, and then my delay is calculated in microseconds and goes up to about 8,000 odd microseconds. So what I do is I do a shift right 5 to divide it by 32, because that's obviously much faster than doing a divide by 5. I mean by 32, unless it's a smart compiler, who knows. And at that point, I then have packed it into an 8-bit byte. And I then set my lines. If the byte is positive, I set it low. If it's not, I set them high. And then I send a signal saying, okay, I'm now finished with it. And that tells the slave that it can then read the other end of those 8 lines. And then this is just, I can tap in, if I don't know if I'll be able to show you this, but okay, the board's not available anyway. I haven't, it's unplugged, okay. But what this does is I can enter an RPM and it will then change the timing, which is how I created those slides, so that I can test the function. So that's the master function. And the slave function. Can you see that okay? I'm not sure if it came. Do you see the slave?
Yes.
No.
Spark slave, it should say at the top, down
No.
there. No? Okay, hang on. Maybe I need to share a different screen. Okay, can you see that?
Yep.
Yep, okay. Right, so same pin layout as before. Some constants for the dwell angle. The dwell angle is basically the length of time that the spark pulse goes down or up, depending. Or in a car conventionally, it generates the spark when you cut off the power rather than the other way around, because well, it just does. So then pin mode, the opposite of the other end, because I'm now on I want all these to receive. So I'm pulling them all up. This one here only goes to the oscilloscope. It's the green pulse on the oscilloscope. And so I don't have a pull up on it. So I actually pull it up on the board. I use a 1.1 kilo ohm resistor to pull it up myself. Okay, so then I initialize my timers. And okay, so I don't know if you haven't programmed an Arduino, there are two parts to the program. I should have said that. There's a setup loop which is basically like initialization in Delphi. And then there's a loop which just runs again and again forever. So this is my loop going round and round and round as fast as it can. And if it sees that a spark out is requested, it starts the clock. And if it can, it reads the 8 lines from the master. It looks to see if they're pulled low. And if they are, so it sets the variable to 0. And if they're pulled low, it ORs them with the various bits in the byte that it's building from those 8 data lines. And then it shifts that byte 5 bits left. So it multiplies it by 32. And then it writes back to say that it's finished reading it and that the master can reset it if it wants to. And then it delays. That's another of these infinite, well, not infinite, but it's a while loop with no subject statement. It just goes round and round and round. Then it reads microseconds again when it comes out of that loop, which means that it's delayed long enough. Sets the pin low, holds it low for the dwell, and then sets the pin high again. And that's the whole lot. That's all the code that does it. Does that make sense? Did that answer your question about the 8 bits?
Yes, I was wondering if you're doing the synchrony by hand sort of thing. The raising a flag, you can read it now.
Yeah.
Raising the other flag, thanks very much, I got it.
Yeah.
Yeah. I was wondering if maybe the hardware was like designed to do that or anything like, or anyway, question answered. Thank you.
Yeah, I mean, actually the serial, you can run the serial mode at up to 115/200. Well, that's the usual USB speed, which is pretty fast. And I kind of wonder in retrospect whether I could have just sent it over USB. But I figured that doing it in parallel like this, the GPIO pins are extremely rapid. And so I thought this was the fastest way of getting the signal across. Because we're down to, at the top end of the engine's range, we're down to like 300 odd microseconds to complete the whole thing. So I didn't want to fool around too much. Yeah. Okay.
I do have a question, Hill,
Yep.
and it's about the delay. As I saw on the client side on the slave, the delay was programmed initially and then was used to decide when to signal back. But I would have thought that the delay needs to vary depending on the RPMs that's coming from the master. Have I missed something, or is there some magic going on that I do not understand yet?
Or did I screw up? Anything is possible. Hang on. Let's have a look at that again. Driver. Sorry, I'm just trying to pull it up.
Yeah.
Oh, Spark Slave, right. Okay, there we are. and then I'll have to share it. Where are we? Let's get rid of. I need to kill that. Okay. Then bring up that. Share screen. Spark slave share. Okay. Right. So, so the timing of the slave is controlled mostly by that. When the yellow signal, the timing signal coming out of the master, so that tells it to start thinking about it.
Mm-hmm.
There's always a bit of a problem when you set the clock, whether you set it before or after, and what's going to be included in and what isn't. Anyway, so we set the clock here right after we've started the spark. We've got our delay. Then we write back.
But by
Okay,
shifting
yeah.
it, by shifting it actually, isn't that a fixed delay now?
Sorry?
By shifting it,
No,
like
because
you do here.
we've brought in a number, say 64,
Okay.
and we then multiplied it by 32 to turn it into microseconds.
Okay, that's the point. Yeah. So that putting it together in the 8 different bits tells us how fast the master is sending that signal.
Yeah, it means that I end up with a granularity of 32 microseconds,
Mm-hmm.
Which is at the top end is getting on for 1 degree of crankshaft rotation, and at high RPM. So yeah, so then it sits there for the delay time. It takes the clock, resets the clock, which hopefully is almost instant, and then it pulls the pin low, which will start firing the spark. And then when it's finished, it just goes back to screaming around, waiting for spark out to go low. Yeah, does that make sense?
Mm-hmm. The only question I have now, if you is that I would have thought that the ignition like that, the slave is actually calculating when it needs to spark, but with having that spark coming from the engine itself decides when it's time. So it's not the
Absolutely.
controller that controls
Yeah.
when the spark happens, but it's more the engine itself, and the controller is only there to set the signal, say it's time, it's time, it's time, it's time, right?
Right.
But calculating
So,
when it's time, it's actually still done in the engine.
yes, absolutely. So
Okay.
this spark out signal at the top here, I showed at the beginning that little device with the optocoupler.
Yeah.
In the version actually on the engine, that spark out signal will come out of that optocoupler, which is triggered by the engine.
Yeah.
Sorry, not out of the model engine that I'm running on.
Yeah, for sure.
Yeah. So that will tie the whole thing into synchronicity.
Uh-huh. That's a bit. I mean, I've never designed an engine, right? But I thought that the idea of an ignition system is that there's a controller out there who's actually doing the maths and the calculation, and there's a fairly dumb engine out there who's just doing and doing and doing, and would try to do what it's told to, or even if it would destroy the machine if the ignition wouldn't be smart enough. But as far as I can see here, the smartness for sending the signal that it's now time to ignite is actually coming from the engine itself. That's the part where I'm a bit astonished, let's say.
Maybe, hang on, I'll just stop sharing this and we'll go back to the presentation.
Yeah.
Okay, see, no problems doing this, I know why. Oh well. Okay, so I know I didn't want to do that, did I? I wanted this. So I want to share the screen.
Paul, we are losing you. You're disappearing on us.
How so?
Paul is actually this. Paul, I'll have to show you. This just arrived the other day. Huh? And it makes a big difference. Huh?
Well, maybe that's the best thing that could be done to me. Okay, so if I just go back here, do you see the graph?
Yeah.
Okay, so down at the bottom right is the distributor. That's what actually controls the engine timing. So that turns at half engine speed. and inside it is a little device that makes some brakes well, it's a 6-cylinder engine. So every 2 revolutions, it makes some brakes 6 times. And that generates the ignition pulse. Okay. And that's the signal that I'm using as the input to my slave. You see, what normally happens is this guy on the end, which is the rotor, goes whizzing around inside here. And there's a weight and a spring in here that actually moves it forward on the axis at high RPM and back at low RPM.
Okay. So that's the mechanical solution to it.
That's the mechanical solution to what I'm doing electrically.
Yeah.
Yeah. And so obviously that's not very sophisticated because it's just 2 springs that control that whole curve.
Yeah.
Whereas I can do much more magic by doing it electronically.
And when you go back to the next picture where you showed us the 3D thingo, right?
That one?
Yeah, exactly. So obviously now a spring is no longer good enough. So we need to have some logic that says, well, if it's just down there at the bottom with the dark blue stuff, I need a delay of such and such. But if it's up there in the red stuff, I need a much smaller delay. So who is the guy who decides about that in your Arduino master-slave environment?
Okay. The system I'm designing will look at manifold vacuum, actually rather like that old system that we looked at. And from that, it can determine the load on the engine by combining that with RPM and everything else. And so that will give me this load axis.
Yeah.
The RPM axis I get just from reading RPM, so that's easy. And then, frankly, you build the map by trial and error. You put the car on a dynamometer and you try the different timings. Different timing and load factors, and build your map.
Yeah. Okay.
And the same thing for the fuel injection, actually. That I have to build a 3D map, well, a grid like this, basically, that will return a value for any combination of load and RPM.
Okay.
So that will happen. That would happen in the more intelligent of the computers, the Beaglebone or whatever it is.
Yeah. So in the end, you do have a table, a decision table that says if it's that RPM with that load, use that delay. And if it's another one, so it's not calculated on the fly in that moment, but it's actually something with trial and error. And once you've established what creates you the best power in each situation, use that as a decision table in your slave.
Right, exactly. So, so what would happen would be I would pass this vertical value, the timing, I would pass that over my 8-bit into the byte, and then the slave will apply that delay.
Good. I shut up. I've just never designed an engine, but I thought that's interesting because it looked fairly straightforward from a slave point of view, right?
Yeah, from the slave point of view, I can't afford to have it doing lengthy computations.
Yeah.
I'd rather get it microsecond correct than have it thinking about things too long. Yeah. I think that's about it for me, actually. Well, I guess I have this one. So I have the option that I could do it with a Raspberry Pi and 2 Arduinos. And obviously the Raspberry Pi runs Lazarus. So I put all the complicated logic there, and also has graphics. Or I could do it with a Beaglebone and get rid of the other Arduino and use those PRUs to do the calculations that I'm performing on the Arduino. Yeah, so that's basically, and I say Lazarus will run on either the Raspberry Pi or the Beaglebone. It's not an issue. I have to say a lot of the code will reside on the Mega, like those delay tables and so on will reside on the Mega, because it will do the calculation of the more complicated things, because I can't rely on a fast enough data flow to the Raspberry Pi. Yeah, which I might be able to on the Beaglebone. Right, that's it. So I hope that wasn't too awful.
Hill, you mentioned earlier that there was a problem with the micro HDMI.
Yeah, it's pokey. It's a tiny little thing. It's lurking just under here. You can't even see it. It's very small and brittle. And also the way they've designed the Beaglebone, There are sometimes you can't use some of the pins and have HDMI. They interfere. So I need to decide whether what I'm prepared to sacrifice and whether it's worth it. Yeah.
Cool.
A while ago, I tended to visit Peter Wolfgram in Perth every year after he moved to Perth, right? And he had actually done some software for a wood shop where they had all sorts of very heavy equipment that's very expensive, and you could come with your project and use the machinery, and he had controllers on those machines that checked if a card was in or out, right? So that's how he charged by the minute for each user, and each card was assigned to a user. Now, his microprocessor programming was happening in a programming language called MicroPascal. And I was wondering, could one use MicroPascal to program an Arduino or a Beaglebone?
You can use, there are a number of languages available. There's Python, C, whatever. I think MicroPascal will run the Arduino.
Yeah.
But the Lazarus runs fine on the Arduino C, which is what I used, I find perfectly convenient. And Lazarus will run on the Raspberry Pi or the Beaglebone and give me, you know, basically most of the benefits of a Generation 3 Delphi.
Yeah, but the thing is that you want to access those kind of registers or these lines separately, and the fastest way to do that with the least overhead was either the C version that you used, right, or possibly a MicroPascal, which knows nothing about objects, knows nothing about multi-threading, but is just a bare bone programming language to make sure it gets up to the speed that you need on a processor like that. And I wonder if you can achieve that with the Lazarus, even if it runs on the Beaglebone.
No, I don't think I could. But I could achieve it with the two PRUs on the Beaglebone, which are running, you know, something rather like Arduino C, just a very hardware-based, straightforward C that can access the registers. Yeah. But otherwise, no, you're right. I wouldn't try to do that 8-bit transfer from the Raspberry Pi to the Mega. I would do all that on the Mega and just transfer it to the Arduino. Yeah. Yeah, otherwise, yeah, trying to do even like serial or whatever on the Lazarus is a bit of a pain.
Not working. I've seen some of the code that he used in his microprocessor, and I can understand this is like you're dealing with registers here, and you're switching on and off, right? And it's very basic, and nowhere near what you do with an object Pascal. Yeah, it's much closer to the hardware.
Yeah, for sure. Yeah, I do. I mean, I have a program that some of you've seen, I think, written in Lazarus that runs a stabilized state laser, and that uses RS-485 and RS-232 and various other conventions to speak to the laser and to the equipment. And it does work okay, but not real time. Yeah. Yeah. Okay.
Cool.
Can I ask, is anyone else using Lazarus here in our group tonight, of you guys? Trying to, okay.
Are you using it, Matthias?
Well, as I said at the meeting for ADUG Adelaide, I needed an excuse to travel to Germany, and Delphi conferences became increasingly difficult to attend, and there's a Lazarus user group, right? And when they run a yearly event, my flight to Germany became a business trip because I joined the Lazarus group, and I became a bit involved with Lazarus. And whatever I tried, I very soon ran into some problems that turned me off. I wasn't really very happy. And one of them was just recently the generics and the support for generics that looked promising at first, but then when you looked at the real implementation, the stuff that looks like Delphi, right, it wasn't working 100%. And the other thing is unit testing. When you're doing unit testing, you may have a design pattern called decorator, and the decorator is responsible for creating an environment for you, and then you run the test case within that environment. But in order to do so, you first need to create the environment and then run the test case inside the environment. Now in Lazarus, when you click only one test case and you run that one test case, it's not doing anything up in the chain, right? So all these dots that are there until you get to the test case are not executed. So all the environment is not there, right? What's that? And when I heard Graham talking about it at ADUG Melbourne, I understood, yeah, he had to create his own unit testing framework for Lazarus, yeah, to make that happen. Yeah, I found that a bit odd. Yeah, and all the people that I met there in Germany, they are hobby programmers. I don't think that any one of them is actually making a living out of programming with Lazarus. Yeah, but could be just a group, right? And who they attract and who they don't attract. I've got no idea if that's representative for the Lazarus community.
I think
Well, one of the other Canberra members, Neville, works for Cyro, and they use Lazarus, don't they?
Yep, he's done quite a lot of stuff in it. It was mostly him, I think, that got me interested in it in the first place.
Yeah.
I mean, I actually find it very good.
Yeah.
I'm writing mostly desktop stuff and for hardware and data manipulation and so on. And I personally, I think for something that's written and by amateurs and is free, it's actually an amazing project. It's very stable. My programs never crash. They run for weeks on end. Yeah. Well, they do crash obviously when I screw up, but put Lazarus on the whole.
Well, maybe I was too ambitious to say, well, yes, I know a T object list, a T object stack of T, right? And let's create an instance of that and let's work with it. And the first thing is you debug the code, you see what the pop creates, and you say, great, I've got my own class coming back. And when it then passes it on to the next higher level, so you can finally use it, it becomes a T value again. Yeah. What the heck?
Well, I did say it's equivalent to about Delphi Generation 3.
Okay, good, fair enough. I always thought it's Delphi 5, really.
Well, maybe Delphi 5, yeah. Or maybe I'm pessimistic. The 3 bit of it's very solid.
Yeah.
It probably depends just what you're doing with it. Because some people, you know, are trying to do really quite sophisticated things with the language and other people aren't. And if you've got a very simple requirement, then Lazarus is probably fine.
Yeah, and let's face it, it took Embarcadero or CodeGear quite some time to get the generics correct too, right? It was not working immediately. Only ask Vincent what he was complaining about it, right? Originally, when he said, oh yeah, let's get it going. No, not immediately. It was not working that well. But now it's working. It's working brilliantly.
I think Lazarus is quite widely used as a teaching language. I mean, maybe community versions of Delphi will undermine that somewhat. I don't know. But when Delphi was very expensive, it made itself rather unattractive for that sort of thing.
So that's what happened to me. I was actually asked by a friend if I could do something for his kids in the school holidays, because lockdown, no one can leave home. So why not having a programming session at home, right? And we looked at Lazarus and I tried to get it going in Lazarus. And it wasn't so easy. And then I said, hey, you know, we've got a community edition. Back then it was 10.3. And he installed it on 3 notebooks. And the kids were programming that little undo project in Delphi Community Edition. And it was working pretty well.
I can't say I find Lazarus more difficult for simple things. I mean, it's very drag and drop and
No, I'm not talking about the look and feel of the VCL in comparison to what they use. It's more like when you look at the generic classes, there's 4 basic classes there, right? But then it says, but if you use that other mode, the Delphi mode, you've got access to these 15 other classes. Go for it, yeah? And then you go for it, and you say, gosh, no, no, don't go for it, actually. Yeah, and if you don't go for it, it's actually quite good. Yeah.
I guess I just don't go for it.
It's just not me that I tried to get used to it, right? And I thought, oh, great, let's use it.
But I might try the Delphi Community Edition again.
Yeah.
It's just that for a while there, you know, Delphi was a lot of money, and I just wasn't going to spend it. I didn't have it to spend. Yeah.
Mm-hmm. No, you can actually. The only problem is really it is still a professional version, so to speak. And this professional in double quotes, right, means that with FireDeck you can't even talk to a database in your local area network. It has to be a local database. So and that is just not really a professional. That is actually not even beginner. Yeah. So
Yeah.
any other tool that is for free would actually at least allow you to talk in the local area network to a database server. Yeah.
Yeah.
Yeah. And Eric, who's just now creating quite a bit of traffic on our new forum, right? He was lucky. He used ADO in the professional version. He started with that before FireDeck became available. So with ADO, he's got no restrictions there. But you never know what is supported in the newer version of MS SQL Server, right? So they definitely won't improve the COM objects that are behind ADO.
Right. Yeah. Oh, and then another disadvantage of Lazarus is that I used to use Nexus
Yeah.
quite a lot for my database stuff, and that doesn't work with Lazarus.
Yeah.
What do you use instead?
I don't. No, actually, I guess, yeah, I guess if I think of doing a database, I tend to shy away from it and do something else. Yeah.
Well, Firebird is actually working quite well in Lazarus. That is actually not a problem. And you can use the embedded version, and then it becomes like the DCU version of Nexus DB.
Yeah. But recently, I say most of the stuff I've been producing to sell to people and so on has been for machine control and hasn't had a lot of use for remote databases. Yeah.
Lots of pretty pictures instead.
Yeah. Lots of things that move and flash in the night and go beep.
Okay, so if does anybody have any final questions for Hill? No?
Is this just a fun project, or is this for one of your cars? Are you trying to do something real?
It's for one of my cars. It's for my old 1976 Porsche, which I actually sort of, it's taken me so long getting this project going. I've actually got it going rather well without the need of the electronics. But I put so much time and thought into it that no, I'm curious. The injection system that's in it is, again, completely inflexible. It actually relies on the shape of a hole to control the tuning. And so it would be interesting to try and make something that was electronic, more flexible. And I can then do things like O2 sensing and so as well, and add that into it. There could be a market for it. There's a lot of cars out there that run that old Bosch K-Jetronic injection, and it's nearly always a problem. So there might be money in it if I get it to work properly. Yeah.
So are you going to incorporate all the fuel injection bits as well into it?
Oh, absolutely. Yeah, the ignition, it was only something I added on later.
Right.
And I thought I was actually rather clever coming up with this idea of mechanically advancing it and then delaying the spark. But I noticed someone else is selling an ignition unit where they must do the same thing, because you jam the distributor as far advanced as it will go, and then it controls the timing. Yeah.
Right.
So it's obviously not an entirely new idea.
And would you have the ability to test the engine so that you can create that 3D model that tells you under which RPM and so on you've got the best power? Because that is something you need to test before you can actually deploy a unit like that.
Yeah, I need to get the car on a dynamometer.
Yeah.
The O2 is easy. I can build that into the system easily.
Yeah, okay.
And
then you would need it for every car, for every model, for every engine size, for every power that the engine has, for which you want to sell it.
Yeah, for each
It's
model.
like programming for a mobile device. You never do that without having the device yourself, right?
Yeah, well, oh God, I think my wife would kill me if I bought any more cars.
And now you've got a good excuse, Hill. Get more of those.
There's actually quite a lot of those K-Jetronic injected old 911s out there. And they're now worth enough money that people are interested in trying to get them to run better and using them more. Yeah. It's one of those systems that when it was brand new, it worked well. But if everything doesn't work perfectly, it doesn't have the flexibility to deal with it.
Yeah.
We'll see. It's a hobby.
Yeah.
Stop keep me out of trouble.
Something to do in your retirement.
Yeah, exactly. Yeah. I'm also casting plastic bits. That's something else I've started working on. Because a lot of the old trim-on cars, you can't get it anymore. So I'm looking at, well, I'm already making plastic bits. You know, like light surrounds and that kind of things you just can't get anymore. Some of them you can 3D print, some you can't. So.
Are you doing them with the 3D printer?
No, I'm not. I think because the problem with 3D printing is you have to have the digits, and getting the digits is actually quite hard sometimes.
Right.
So I'm actually doing it with silicone molding. I think I end up with a tougher product too.
Yeah.
Will you be able to buy stuff like that? Because I mean, I remember when FireMonkey came out, and we looked at it for my girlfriend. She's running a TCM clinic for acupuncture. I thought, wouldn't it be great to have a person, a male and a female, that you can turn around and you can place the needle and you document it that way, right? And then when you pull up the record from the last treatment, you're not only seeing a list of acupuncture points, but you see a 3D model turning around where the needles are sticked in. Now, buying these models is really, really, really expensive.
You mean buying the digits?
Yeah, exactly. Getting the model that represents that person, right? And I think in your case it would be the digits for the mold, right? That you need.
Yeah. And the first bit I'm making is I don't know, maybe 1/2 meter long. So it's a bit big to 3D print anyway.
Yeah.
So silicone seems the way to go. I know. We'll see. I'm actually getting pretty close to a saleable product. So then we'll try selling it and see what happens. Keep
Or
the
else,
tax man happy.
if that doesn't work, you could always go into business making the digits and selling it to other people to make.
Yeah, I guess you'd have to have a laser scanner or something, wouldn't you, to do something like that? Which I think is a fairly expensive investment.
Yeah. Okay, well, thanks, Hill. That was very interesting and a bit of a change
Thank you.
from our Delphi brains. So that was really good. I enjoyed it. And
Thanks a lot.
you do know how much it costs to replace a Porsche engine if something goes.
A lot of money these days. Holy cow, a lot of money. I should be careful.
Yeah, I had a really nice BMW motorbike, right? And the clutch was in need of repair. No, the gearbox was in need of repair. And I looked up what you need to do for that, and doing it at the dealership cost you an arm and leg. That motorbike was 10 years old, right? So now it's been replaced. And for the price that I paid for a BMW, could I buy 3 of the motorbikes that I've now bought?
Yeah.
So
I think my engine is worth like $15,000 or $20,000 or something just for the engine.
Wow.
Yeah.
So yeah, I shall try not to explode it.
Okay. So be cautious with your own ignition then.
Yeah, be cautious with everything. Yeah.
Okay.
Test it
Have a
on
nice
somebody
evening, everyone. Bye-bye.
Good to see you all again.
Yep. Okay.
Thank you for the meeting.
Thanks, Hill. Don.
No problem.
See you.
Bye.
Paul.
Good night.
Thank you.